Also, just to quickly say, the certificate ceremony is not in this classroom. It's in SEEK 233. So make sure you guys put that in your calendar, that you guys are coming to SEEK 233 next Friday at 5 p.m. Don't come here, don't come to the CS building. That way you guys make sure you get it. And we'll also put an announcement on the Discord.
Because in that room we can play games, we'll have snacks and everything. It would be more of like a chill environment, less like a lecture hall sort of thing.
Yeah.
It is a ceremony after all, we all job and we like celebrate together.
Yeah. It'll be a fun time. Everyone will be chatting. It'll be good. We'll bring some board games. If you guys have any board games and stuff like that, bring that also. Or if you have any like leftover snacks you want to share, feel free to bring that. It should be fun. Yeah. So yeah, to start off with today we're going to talk about like the introduction of like language modeling. What is it? Kind of talk about some foundational concepts that you guys should know. And we'll talk about sequence modeling. So how do language models predict sequences and figure out what's going to come next? And as well as talk about some of the architectures like recurrent neural networks and transformers and that kind of thing. And we'll go into more advanced topics like RLHF, which is like reinforcement learning with human feedback. So to start off with the introduction, what is language modeling? Actually, does anyone have an idea of what language modeling is first off? Maybe raise your hands. I also give you guys a peek, so yeah.
It's like, wait, I was just answering yes.
Oh, okay. Yeah, okay. Does anyone else have an idea of like what language modeling is? Or actually, let's just have you guys raise your hands. You don't have to answer what it is. You could just tell me if you have an idea of what it is and raise your hands. 4. Okay, we have like 2, 3-ish, 4. Okay. And then the people who like kind of raise their hands, you guys don't want to say like what you kind of know about language modeling? Okay, yeah.
Like maybe like how like they understand like human language and generating human language, kind of what ChatGPT does.
Yeah, perfect. So ChatGPT is an amazing example, like kind of understanding like what languages mean and then kind of interpreting that. Yeah, that's a great example because we'll talk about this later, but basically the way that computers understand this is through like vector representations that they kind of have of like the words and their meanings. And then that's kind of like how they plot them in vector space. So here's like the official definition to put in your notes, but basically language modeling is like involves predicting the sequence of a sequence or predicting the likelihood of a sequence of words or tokens, which forms the foundation for a lot of powerful applications like text generation, translation, sentiment analysis, and conversational AI. So like ChatGPT is a great example, Gemini is a great example. Just like any AI platform where you're kind of communicating and it's understanding what your text means, that is like an example of language modeling. It's like the process of building computational systems that can like understand and process language. And at its core, the way that language models do this is by learning the patterns, grammar, and context from the vast amount of data, right? So by doing so, they can produce text that's not only coherent, but it also is contextually relevant. So they rely on the statistical patterns in the data to predict the next word or like the next token within the sequence. And this was like an issue in between because like language models weren't able to kind of understand like the context of the conversation. So if you had a message like 5 messages up in your conversation, it would forget that context. And then like if you asked a question about that later, it would be pretty bad at it. And ChatGPT is still kind of bad at this. If you've ever asked ChatGPT a question, like let's say like 10 minutes ago in your conversation, and then you ask it something new, sometimes you'll get something random. Like I think I was telling Misha about this example, but I had this one chat with ChatGPT and I forget what I said. I asked it some random question, and I think it was like something with like CS or math or something, and then all of a sudden it started talking about real estate prices, and it had like an entire conversation about like real estate prices and like phone numbers and stuff like that, and it just came out of the blue, right? So that's kind of like one example about how like, even the super powerful tool, there's still a lot of holes in language models. But yeah, there are 3 primary features you can kind of break language modeling into. The first one is prediction. So what is prediction? It's one of the most fundamental tasks, which is just predicting the next word or the next token in that sequence. And for example, if I say something like the quick brown, you might default to the next word being fox. Or, can you guys give me like a sentence? Like the cat in the hat or like something like that? Okay, let's get like an adjective. An adjective is something that describes another thing. Yeah. So we can get like a color. Yeah. Fluffy. Okay, awesome. And then does someone have something that's fluffy that they want to like raise their hand and say? Come on, you guys. Yeah. Cat. Awesome. So fluffy cat. Is there another word that you guys think could go with the sentence fluffy cat? And it would be contextually relevant. You guys are really smart? Yeah. Yeah. Orange? Okay. So orange, fluffy cat, awesome. So basically, like, as a human, when, the first person, she said cat, and then the next person says fluffy, next person says orange. All these words kind of contextually make sense, right? So in terms of language modeling, it's kind of like having that computer also understand that contextual significance of how do these words relate to each other, and then what makes sense in the way that it makes sense to humans. And these systems learn from really large data sets, which enables them to kind of learn that syntax, that grammar, and that context, and even understand like deeper meanings within a sentence or conversation. For example, they don't just predict words randomly, right? Like if you're texting someone and if it predicts the next word, it's not just generating like a random word and saying, hey, you can use this. It's using that based on your conversation history, based on your textual history, and based on the history of like many users who use those same applications. And in terms of applications, first off, we talk about ChatGPT. Chatbots like ChatGPT can engage in very natural sounding conversations. Like if you talk with ChatGPT, sometimes even now it's like too friendly and it's using emojis and stuff like that. But sentence-wise, it's making sense, right? It's not like it's someone who can't you think doesn't know English or something, right? So it speaks it properly. And even search engines use LMs to provide relevant results to queries. So if you guys Google something on Google, sometimes it is using those keywords and it's searching those, but it also understands the meaning of what your search is to give you other relevant results. And another thing is language translation tools like Google Translate, which translate from one language to another. So sometimes there isn't a direct one-to-one, right? So in English, you might say one word, in a different language, you might say another word, but understanding the meaning behind that word so that way you can translate it and have that also be accurate. So by combining this type of prediction, contextual understanding, and real-world applications, language models have revolutionized the way that we think about technology, right? So they enable us to assist with communication, creativity, and helping people, etc., and even understanding user intent, which makes them a really important part of AI systems. So the next question we're going to kind of discuss is, are there any other examples of AI applications that involve language modeling? And then what have you guys used? So there's ChatGPT. You guys can also Google things. Maybe turn to your neighbor or turn behind you and discuss examples and Google things, and then we'll do that for a minute. And then I expect people's hands to be raised. Yeah. And if there's a seat between you and someone else, just scooch. Yeah.
If I don't take conversation in the next 5 seconds, I'm coming and I'm making friends.
Yeah.
Sign on that.
I know. It's gross. Yeah. I like your two-player games. Yeah.
I'm doing a lot.
Yeah. Here's me. Yeah, not more people. We could switch AI mix of this.
Oh.
Yeah, but we also yeah. But I'm and it's always practical. Yeah. I think next year when I update the presentation, I will switch. Yeah. Or see someone else wants to update it. Yeah. Shut up, mission. Okay, it looks like some of the conversations kind of died down, so I'm gonna ask people to raise their hands. I heard a lot of good chitter chatter. No one looked like they weren't talking the whole time. So, what are some examples you guys kind of came up with within your groups? I'll take 3 and then I'll move on. Yeah.
Like the customer service robot.
Yeah, that's a really, really good example. These days, a lot of customer service things are getting automated. So I don't know if you guys have looked into housing or stuff like that, but sometimes if you're reaching out to businesses and stuff, the initial emails you're getting are from a bot. They're not from an actual person. So I know for me, in between, I was reaching out for real estate stuff, and then I got a text being hey, you've been talking with our AI bot Lainey, and I had been messaging that bot thinking it was an actual person, right? So a lot of conversational things are a really good example of LLMs. Is there something else that you guys have kind of thought of as an example? Yeah. Oh yeah, image captioning and video captioning. That's a really good example because it's understanding what's going on within that image and that video to kind of give the sentences that make sense. Yeah. And then let's get one more example. Yeah.
There's AI flashcard generators, where you type on what class you take or something, or topic, or generate a bunch of flashcards.
That's a really good example, AI flashcard generators. So if you type in a prompt, it'll give you a lot of flashcards. And then do you have a question?
I was wondering, Those like AI software where they take in text and like the output like the text is spoken in like someone's voice. Does that also count as a model?
Yeah, I think that counts because there's like this whole area of like speech to speech kind of research that's going on, and that's used in LLMs, where it's what you're saying, like they put in text and output speech, but it takes LLMs to convert that speech into something that can be understood. And that's like actually a whole other area of research where you can examine sound waves also. And instead of like taking speech and translating that into text and then translating that and then translating that back into speech, like let's say you have like English and you're converting it to Spanish. Instead of converting like English speech into English text, and then translating English text to Spanish text, and then translating Spanish text into Spanish speech. You can take the English speech and take those sound waves, and then get models to kind of understand what those sound waves are saying, and then just translate those sound waves into other sound waves. And that's like a whole other area of research. It's called like speech to speech. But yeah, that's also an example of LLMs, even though it's like with audio and stuff like that. And if you guys have more questions about that, you can talk to me about that as well, because that's like one of my areas of interest. But yeah, so these are really good examples of AI applications. And yeah, next we're going to move on to some foundational concepts that you guys should know about. So the first one is tokenization, and the second one is word embeddings, and the last one is an example. And this picture is a hint of your example. So what is tokenization? Why is it important? So tokenization is essentially like the first step in natural language processing. Unlike images or numbers, text doesn't naturally just translate into something a computer can process, right? Like if you guys have taken like, more of like a hardware class or something like that, you've probably seen how like computers don't just get passed in text, they get passed in like numbers. So tokenization solves this by breaking text into smaller, more understandable chunks for computers that are called tokens. So why is it necessary? Models like GPT and BERT only understand numbers, right? So tokenization bridges that gap by converting that raw text into numerical data. And without it, the models wouldn't be able to understand this text and understand what it means. So in terms of the applications that impact, this process directly impacts like the efficacy and the accuracy of these models. For example, subword tokenization helps the model recognize parts of rare words, and this also improves its ability to generalize and understand context. So tokenization, as I talked about, first step in the NLP process. And depending on the approach, this step can significantly impact how a model understands and processes language. So the three main types of tokenization we're going to talk about today are word level tokenization, subword level tokenization, and character level tokenization. So in terms of word level tokenization, it basically just splits the text into individual words, basically exactly what the name says, right? So for example, if you're saying something like tokenization helps, it's going to split into two tokens, of one token being tokenization and the other token being helps. And it works well because it's very simple, it's very intuitive, and it works well when the words are distinct and straightforward. So, that's like a major plus. However, it does struggle a lot with more rare and complex words. So, for example, let's say you had tokenization, that might not exist in your model's vocabulary, right? Like maybe your model doesn't have every single word that exists. So then if you throw in a new word that it's never seen before, it's going to be like, hey, I haven't seen this before, I don't understand what this means. And if it doesn't recognize the word, it can be considered out of vocabulary, which can limit understanding. The next thing is character level tokenization. So this goes a step further and it breaks down words into every single character within that word. So earlier we said like orange fluffy cat, right? Character level tokenization would split that up into like O-R-A-N-G and like have that each of those letters be its own token. And this level tokenization completely avoids that issue of out of word characterization or out of word vocabulary issues that you could have, since every character is always recognized. Like in the English language, you only have 26 characters, right? So no matter what word it is, if you've never seen it before, it's always going to use those characters. So it's really useful for handling like more informal language or creative spelling. So can you guys think of like some acronyms real quickly? If you're texting someone, if you don't write out the whole word, what are some acronyms that you guys use? Yeah.
GN for good night.
Yeah, GN for good night. Awesome. So like if you fed that into a language model, right? And if you were just like GN, it might be like I don't know, like it doesn't know what it means, right? But if you have character level tokenization, this means for like different abbreviations like ATM at the moment, GN good night, GM for good morning, it could learn to understand that context over time, even though it actually isn't in the English language. So this is like one example of where character level tokenization would be really useful. And subword level tokenization is kind of like a nice combination of these two methods. So instead of just breaking it up into every single character, which can be really costly and time consuming, or instead of having it be in words, which could mean that if it's not in the vocabulary, it can't even understand what's going on, we have subword level tokenization. So what does subword level tokenization do? It splits those words into meaningful parts or subwords. So instead of splitting it up into individual letters, it could split it up like in 2 or in 3, and then understand what those subwords mean in context of those things together. So for example, for tokenization, that could split into token and ization, right? So it's something with tokens, and then you're izationing it, you know? So something like that. And this approach is really, really effective because it both balances scalability and also efficacy, because it's both efficient, where it is helping the model understand what's going on, but it's also flexible because it can work. And even if you don't have that word in your vocabulary, there's a good chance that maybe you have a word that's a subword of it, right? So in our original example of tokenization, when we were like, hey, what if the model doesn't have tokenization in its vocabulary? If you have something like subword level tokenization, it could say, okay, I recognize the word token, and I have ization in my database. So this probably has something to do with like tokens and like, splitting things into tokens or something like that. So it's slightly more complex to implement though than the other two, but it's really, really widely used in NLP models, and BERT and GPT use these, by the way. So why do we care about tokenization? So as shown in the benefits row, tokenization is really important because it shows how models can process distinct and informal text. So word level tokenization, as we've said, works for clear and distinct words, whereas subword tokenization works a lot better for capturing complex structures. And character tokenization works well for informal context, so for example, like the acronyms, etc. But it lacks overall semantic understanding, because if you just feed it like ORANG, that might be hard for the computer to understand if it hasn't seen that word before. It might just like, read those at face value and not really understand the meaning. So yeah, I think usually subword tokenization is kind of like the way to go. And let's walk through how tokenization leads to embeddings and dive deeper into like what these numbers mean and how they're generated. So first, let's take the sentence, I love tennis, right? So every single token in this sentence represents a word or a punctuation mark, and these words or punctuation marks are then processed by the model. The model, as we've said, like doesn't understand words directly. It doesn't really understand like what these things mean, but it only works with numbers, and that's where embeddings come in. So for example, after we have those initial tokens of like, I love tennis, each token is going to be transformed into a vector of numbers called an embedding. And can someone explain to me like what a vector could look like? Or like what's the brackets? Are there brackets in a vector? Or maybe like, what is a vector? Let's have that be a question. If anyone's taken like physics or linear algebra, you should know this. Wait, let's get a raise of hands. Who's here has taken physics before? Okay, who's taken like some type of like calc-based physics class? Okay, who's taken linear algebra like 208 here? Okay, all of you guys know what a vector means. What's a vector? Yeah.
It's kind of like a list of numbers.
Yeah, perfect. So a vector is like a list of numbers. And a lot of times, like let's say you have a vector that's like 0, 1, right? This could be something like, if you have like brackets and if you have like 0, 1, that you can kind of represent that as like an arrow. So if you have like x represent that 0, y represent that 1. If you're like plotting a vector on a graph, a vector is basically just gonna be like an arrow. So if you have like a graph and if your vector is 0, 1, it's just gonna go to the right 0, so it's gonna stay here, and it's gonna go up 1, so then it's just like an arrow pointing straight up. And then the more dimensions you add to the vector, the more complex your sphere has to be to plot it. So if you have like 3 elements in your vector, then you're plotting it in 3D space, right? Because you could have like x, y, and z, and then you're plotting it somewhere in that dimension. So basically that's what I'm saying when I mean vector, is that it's like this like list of numbers, and each part of that vector is like representing some meaning of that word. So for example, if we have like the word like love or something, let's say you have some part of your vector that's something with like positive meaning, right? So maybe that part of your vector is like, let's say like the third element in your vector, so the third number in your vector, it's going to be pretty high, right? Because like love is like a positive thing. But maybe you have something else that's like color. Color might be like halfway high, because usually if you have like a heart or something in a book, it's usually colored red, but it's not going to be as high as like the meaning of like happiness or something. So the vector might look random, but you would have like a vector like I, love, etc., where like every single one of those numbers corresponds to like some meaning, and that meaning helps the model conceptualize what that word means. So each part of the vector is going to capture a specific property or feature, And one dimension might represent like how positive and negative the word is. One other dimension could represent the word's relationship to another word, like maybe its relationship to emotions. And another dimension might maybe encode its grammatical structure, right? Like maybe there's some dimension that's saying like, oh, is it like a noun? Is it a verb? Is it something else? And then that could be another dimension of the word. So another dimension could also be like its frequency in the language. So if you have something like the or that could also be a dimension of like how often does this word appear in the English language, so that way you can kind of conceptualize, is this like important or is this not important? And all these numbers are learned during the training of language modeling. So when you're like training a model how to understand these meanings, the model is exposed to like a bunch of text. And through techniques like gradient descent, which we've talked about earlier, it adjusts the numbers in these vectors slowly, so that way you know what the meaning is of each of these embeddings. So that way, like in the vector space, right? Like I described it earlier, if you have something 2D that's like 0, 1, it would just be like an arrow on a graph, right? If you have 3 dimensions, it would be like a sphere. So let's say, this is really simple, but let's say you have like a sphere, and then this is kind of like the vector space of your language learning model. Then when you're plotting these different meanings, the vector arrow that's pointing for a word like love, and then the vector arrow that's pointing for another word like adore, would look very similar on your spherical representation of that vector space, because they both have similar meanings, right? So like one vector might be like 1, 0.9, 0.8, and then one other vector might be 1, 0.8, 0.9 or something, right? So those both of those arrows within that sphere are going to be in a very similar place and also plotted to a very similar place. However, if you have two words that have opposite meanings, like love and hate, maybe those arrows would be orthogonal to each other. Like maybe one arrow would be going this way and one arrow would be going this way, because they completely point in different directions, right? So this is really simplified in like a three-dimensional vector. However, if you have like more dimensions, like over here, you can see that there's like at least over 5 dimensions. That sphere becomes like more and more complicated and more dimensions, and each of those dimensions represent more and more meanings. So why does this work? By training on billions or millions of sentences, the model learns these patterns and learns how to recognize different things. So it might recognize like similar contexts also, right? Like something like I love tennis might be plotted in like the same area as maybe like the name of a tennis player or something, right? Like maybe if you had like the words like Serena Williams or something together, that would be plotted in a very similar place as I love tennis, right? And this also allows the model to capture nuanced relationships like king plus or king minus man plus woman equals queen. So I think, oh, maybe that's on the next slide. But basically, let's say you have like a word like queen, right? And you want to represent this in terms of other numbers, in terms of the vector representation. You could actually take those vectors that represent like king, and you could subtract king by man, like that vector representation, and then add man by woman. So you're taking a king, subtracting man, adding in woman, and then that should plot to roughly the same place as the word queen within that language model. So you can represent words with these types of relationships, like numerically, like almost like how like a computer would with like the different numbers. And these embeddings are really useful to understand both like the meaning and the context, because while a model generates and processes these things, it doesn't just see like a single token like love just being thrown in there, right? It sees like a complicated embedding with like a bunch of different numbers that represent different meanings. And this is what's allowing the model to understand what's going on, and it decodes everything that the model has learned about this word. So yeah, and here's a diagram. I love tennis. Each of those things are corresponding to a vector, which as you can see is like a list of numbers. And this also includes things like punctuation. So yeah, if you guys had to tokenize a word, what would you break it into? Words, characters, or subwords, and why? And we kind of talked about this earlier, so. Okay, let's have you guys raise your hands if you guys would want to tokenize it in terms of words. 1, 2, 3. Okay, and then raise your hands if you want to tokenize it into characters. 1, 2. No 3. Okay. Oh, and then raise your hands if you want to tokenize it into subwords. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So all 3 of those things have like different use cases and stuff like that. I think I was being pretty pro subwords, so that makes sense. But there's no wrong answer. There's just like different trade-offs with different methods. So like maybe if you had like something looking at like a text chat or something, or on Snapchat, maybe you'd want to have that have more of character level tokenization, just because people use more acronyms. Versus maybe for an email, maybe something like subword tokenization might be better, because on an email people maybe aren't saying like ASAP, or maybe they are saying ASAP, but maybe they're not saying other acronyms like good night or good morning, So yeah, it just depends on the context, and it also depends on how much complexity you're willing to kind of embed into that model. So, oh yeah, here's a really good example of how language models aren't always like understanding everything. So basically, this was like on an old version of ChatGPT, and I think I said this last quarter as well. But basically, if you asked the older model of ChatGPT how many R's are in strawberry, ChatGPT would output back saying that the word strawberry only has 2 R's. And I think they patched this in one of their more recent versions. I forget if this is 4.0 or something else. But can someone tell me why you think that if you're asking ChatGPT, who is like, the super smart model, can tell you about like a lot of different things that humans wouldn't know off the top of their head, why does it think that strawberry has 2 R's? Yeah.
Because it like converts this word to like a vector, which might not represent like the letters.
Yeah, that's a really good idea. Like it converts the words into a vector, which might not represent ideas. Yeah, I agree. And I feel like that also leads to like a lot of things where, sometimes like even if it is like a thing of numbers, you might not fully understand the context. So yeah, that's one really good idea. Does anyone else have any other ideas? Yeah.
Maybe like look it into like subwords like straw and berry.
Yeah. Yeah. Okay, great. Yeah, those are both good ideas. Yeah, so I think in this case, what was happening was like the thing of the subword tokenization, where it was looking at the word straw, it was looking at the word berry, and it just broke those up into 2 tokens and was analyzing those like one at a time. And then most likely what happened is like berries after straw, so it just took that second sub token of that word, and then it just looked at that and was like, okay, hey, this has 2 R's, and then it just returned saying that the word strawberry has 2 R's, right? And it forgot about the fact that there was one token earlier in that sub tokenization that had 1 R. So yeah, this thing went viral in AI Reddit, but yeah. And here's like a new model, which, okay, so the mistake is in 4.0 mini, but I think ChatGPT 4.0 was able to tell me that, if you asked how many R's are in strawberry, it was able to say that there's 3 R's. So I guess they patched that mistake. But yeah, so I think, yeah, I explained this better here. But the reason why it struggles with counting the letter R in strawberry is because, yeah, that starting letter is, oh wait, let me see this. Okay, yeah. That's pretty much similar to what I said. So yeah, the starting word is like strawberry. It asks it to count how many times like the letter R appears, and the GPT processes the text by breaking the word down into tokens. And both of you guys are kind of right. So like number one, it's breaking it up into subwords. Like maybe it's like whatever, and then it's also splitting it into tokens. Like let's say it's splitting it into something like 496 and like 675 or something, right? So this tokenization process is optimized for like getting coherent text and understanding coherent text, but it loses a lot of the granular character level detail that's required for doing things like counting letters. So as I said earlier, like ChatGPT and BERT, these are examples of models that use subword tokenization, right? So since it's using subword tokenization, it's not looking at it at the character level, where it could count like, okay, strawberry has 3 letters because it's like STRAWBERRY, but it's looking at it at a subword level where it's splitting it up into straw and berry in this case, right? And that's because that leads to the model generating incorrect answers, like 2 instead of 3, instead of the correct answer, because it doesn't have that capability to just like go through and like count every single character, because that's not how you're feeding it into the model. So the way that 4.0 was able to perform better than, or 4.0 was able to perform better than 4 was likely because it was probably integrated with like better reasoning and like symbolic tools, which made it more capable of resolving tasks on a more detailed level. And it could have also been a combination, right, of more traditional language-based modeling methods or token-based modeling methods with enhanced like reasoning mechanisms, which maybe bridge that gap between like those problematic predictions and logical precision. So I think GPT 4.0 also has Python programming abilities built in. So sometimes if you guys like ask it a prompt, you can see like ChatGPT is like thinking, and maybe you see like code pop up if it's like something like, I think at some point I was taking like CSU 351, so I needed to like have like 50 zeros because like I needed that for my like bits or something. So I didn't want to type out 50 zeros, so I just told ChatGPT to give me 50 zeros, and then it didn't give me 50 zeros, right? I think it was like 48 or something, and I was like, hey, like why can't I do this? But when it was like generating this thing, it used Python code to like have like a for loop or something that gave me zeros, because I could see it like thinking, and then it like gave me like 48 zeros instead of 50. But basically, the difference between 4.0 and 4 is that it leverages like those Python programming abilities to answer some questions, which could even be like word prompts and stuff like that, or count letters accurately, which could provide like a workaround for such tasks. So instead of ChatGPT actually like on an LLM basis taking in your subwords and counting in those letters, what might be happening is it's just using Python code, and then it's just using that code to count the letters in like a programming kind of way. So yeah, and then we can talk a little bit more about word embeddings, and their significance in understanding like relationships in between words. So what are word embeddings? Word embeddings are just like those numerical representations of those words, and it kind of helps capture like their meanings, relationships, and cultural nuances. So there's two primary types of embeddings. So one type of embedding is static embeddings, and the other one is contextual embedding. So what is static embeddings? Static embeddings are things like word2vec, and if you guys heard of it, it basically just assigns like a fixed vector to a word. So if you give it a word like butter, it's going to be like, if it has like a vector that's attached to it, that vector is just going to be something like 0.9, 0.7, 0.6. And then it's always going to be that, right? Like anytime you give it this word, it's always going to return back that same vector, regardless of the context. And this is nice because, you don't have to, it's a lot less complicated because every word just has one token and it's pretty easy to use. But you can kind of see how, if you have like a word like riverbank, maybe it's like splitting that up into like river and bank, and then it's just kind of saying it like very like literally, like this is like a riverbank, or sorry, if it has like the word bank, it might interpret that as being bank as in like the token embedding of like a financial institution, or it could interpret bank as being like the token of like a riverbank, right? So some words don't always have like the same fixed context because they can be in different words. Or if you have something like butterfly, maybe if it's like interpreting it literally, it could be like a butter that flies, instead of being like, hey, it's butterfly. So that's kind of like one issue, which is why we have contextual embeddings. And these are the things that are used in BERT and GPT, which provide word representations based on the surrounding words in that sentence. So instead of the token just being one-to-one, you give it a word and it gives you back a token. That token is based on the surrounding context of that word. So the word bank would have different meanings based on the usage in that sentence, right? So if you say something like riverbank, maybe it would say like water or river. So then the model would say like, hey, even though you said bank, it's actually going to be pointing into the same direction as like a river would in the token space, instead of at the same place as like a financial institution. And I think, yeah, talking about the king minus man plus woman equals queen, basically showing how you can mathematically represent these words in language learning models. And if you're also thinking about like embedding brainstorming, you can consider these kind of things as a way to just map these words onto high dimensional space where similar words are closer together. I think I talked about this earlier, but yeah, like something like dog and cat would be mapped close together, while dog and car might be mapped like farther away. So we can also talk about another embedding example. So let's say we have like doctor minus hospital plus school. What's like a word that you guys think the model could think it is? And there's also multiple right answers for this, by the way. So like, let's say you guys are all LLMs, and I just gave you doctor minus hospital plus school. What does that equal? Yeah.
School nurse.
School nurse, awesome. Yeah, school nurse. Any other ones? I think I thought of like 3 more, so there's at least 3 more answers. Yeah. Teacher, awesome. Okay. That was one of my 3 more. So there's 2 more answers. Yeah. Med student? Oh, that's really good. That wasn't one of my 2 more answers. So yeah, that's good. I think we got 3. Yeah, we can move on. But basically, summary for this slide is just that word embeddings provide this type of foundation for natural language processing. So this is what basically allows models to kind of interpret and generate that text with that kind of accuracy and relevance. And that's kind of like, I guess the basis of how that works. So now for a discussion question, why do you guys think embeddings are critical for understanding the relationships between words? I kind of just said it, so, if you guys were listening. No, I'm just kidding. But yeah. And I think there's multiple right answers to this as well. So I'll take like one. Maybe I'll have you guys like raise your hands. So raise your hand for like what you think is maybe like the most impactful reason for models to understand the relationships between words. So do you think it's like capturing like semantic relationships, or like contextual understanding, or like overcoming those like vocabulary limitations where if it doesn't have like the word in its dictionary, it could still understand what that means. So who thinks it's capturing semantic relationships? One person. And then who thinks it's understanding the context in which the word was used, like that contextual understanding? 2, 3, 4. And then who thinks it's overcoming that vocabulary limitation? Okay. Everyone else, what do you guys think? No, I'm just kidding. But yeah, it's like those three things, right? And there's also other ones it can have it can have good reasoning. So if you're like translating something to something else, the relationship to like Paris to France might be the same as like Tokyo to Japan. So that way it understands like, okay, if you have like a city to something to a state, that could also be like a relationship between another set of words. It's also important for multilingual tasks. So that way, even if you have like the vector representation for like cat in English or like gato in Spanish, which is just like cat in Spanish, that would be very close in the shared vector space. So that way, like in translations, like those would be more accurate translations. And it also can improve model efficiency by compressing that information about words into very like dense vectors instead of having those vectors be super far out. And this also helps reduce the dimensionality of that data by making the training faster and the memory usage lower instead of something like a sparse representation like one-hot encoding, which one-hot encoding is like very easy to use and it is pretty effective. But if you can do like more vector representations, a lot of times that is faster and it's also a little bit more accurate. So yeah, the next thing we're going to talk about is sequence modeling. So this is kind of the process of sequence prediction and how models like GPT generate text step by step. So yeah, I should have probably changed this example, but basically the model in this example starts with Arya's best teacher. So what's important here isn't just a string of words for the model, but it represents a series of tokens, and each of those words is mapped to a numerical vector. So instead of so in terms of sequence prediction, right, it's wanting to predict the next word in that sequence. So the model is going to consider all of the patterns it's learned from its training data, right? So for example, it might know that a phrase like best teacher is always followed or is often followed by a descriptor like ever. So this is where it kind of gets interesting because instead of the model just kind of guessing what the next word is going to be, where if I say like Misha is the best teacher, it's going to immediately say like Misha is the best and then just fill in teacher. It's going to generate like a list of probabilities of what that last word could be. So maybe it says like teacher has like a 60% probability, but maybe it has like student has like a 30% probability, and then maybe like friend has like a 10% probability, right? So it's going to generate like what that last word could be and have like a list of probabilities of that last word. And then maybe it'll pick the highest one, or maybe it'll pick the second highest one. But that's why if you ask ChatGPT a question, it's not giving you like the same exact answer every time, right? Like if you say like, hey, is the sky blue? That sentence it gives you back is going to be different on different people's computers, and it's going to be different on different chats. And why is that? It's because ChatGPT isn't just taking in your context and then giving you like a sequence that's like 100% like always like determined right after, but it has like that probability, which makes it a lot more human, where like if you ask it a question, it could phrase that question's response in like a different way. It could give you a slightly different answer because it's calculating what to say based on like a series of probabilities to predict what's later in that sequence. So for example, in this example of Arya is the best teacher, it could consider ever as the last word, but it could also consider other options like because, like if you want to have more into that sentence, or something like and, like Arya's the best teacher and something else in that sentence, right? And this is also how it prioritizes likely completions because ever might have a high probability because it's just a natural extension of that phrase, but words like and might have a lower probability because maybe in this instance, Arya's best teacher is just like the end of that paragraph, so it makes sense for it to not fit that context as neatly. And this is kind of the iterative nature of it because, let's say like you're texting someone, right? And you have like those words pop up at the top of your text bar and saying like, hey, like this word is the most likely next word. If you keep on clicking, like Ari's best teacher ever, and then you click like the next word that your texting is giving you that you should predict, it might calculate, and it'll probably calculate like another probability of distribution based on its data and your own personal data of what the next likely word would be. So like if it's like Misha's the best teacher ever, then the next thing could be like maybe a comma, it could be an and, it could be a because, but it'll kind of calculate that over time. So this step-by-step process is continued over and over again of predicting the probabilities of the next tokens, and then having you pick maybe the next one if it's like that text example, or just putting in like one of the higher probabilities until the model is explicitly instructed to stop, or until it's like produced a specific number of tokens. So with ChatGPT, like maybe it's saying like, hey, you should fit all these responses within like this textual limit, or fit these until it's like contextually makes sense to end this response, and then it kind of like ends that response. So yeah, and I think here I have like this math thing is basically just saying that. So if you have like P, W1, W2, whatever, these are all like words, right? And it's a probability of those different words. And the first word could be like Arya, right? And then that's like W1. And then W2, based on W1, is condition on W1 is basically saying that, hey, now that I've given you this word Arya, what is that second word? And what's the probability of like what that second word is? So it's giving you that probability. And then the third thing of W3 conditioned on W1 and W2 is basically saying that, hey, now that you have like Arya is, and that's your first word and your second word, then what's the probability of what your third word is going to be? And that's going to be like the list of probabilities. So basically it calculates each of those like probabilities like over and over again for like each of those words in that sequence, and then it generates that over time for like on whole or on net, what is like the most like accurate, or what's going to be most likely the response. So we can also focus on autoregressive models like GPT. So what are autoregressive models? Autoregressive models are things that predict a text like one word at a time. So they don't just try to generate each sentence one at a go, right? Like if you see something like Gemini like producing text, it's not just going to give you like a sentence and then give you another sentence and then give you another sentence. You can see it typing in like word by word and just like uploading that up, right? And that's because they're building it step by step. They're not just like uploading everything. And the way that they do it is they look at your given context and your starting sequence, and the model then just predicts the next word based with the highest probability based on that context. So after each word that it predicts, it updates the context that it already has in its thingy by adding a new word to the sequence. So the updated sequence becomes the input for the next word. So if I'm saying something like Misha's the best teacher, it would start off with like Misha is, and then is going to be that context, and it's going to predict the next word, best, and then best also joins that context, it predicts the next word, and then it's going to be like teacher. And then teacher is now that context, right? So that way when you're adding new words, it's not just like looking at the last word and then saying what the next word is going to be, but it's looking at that last sentence up to date, and then it's saying, hey, based on this sentence, what is this next word going to be? And this is kind of leading back to that issue I talked about earlier, where if you have a really long conversation, it might forget what happened earlier on, because over time, this contextual history is going to get weaker and weaker in the hidden state as you're predicting new words. So that's why things that are more farther up are going to be worse. But as you can probably see, it's getting better and better, where with like models like ChatGPT, now it is sometimes able to kind of remember, like if you said something 2 messages ago, it can sometimes remember that because it has that saved in its hidden state. And it's this kind of iterative nature which enables GPT to generate contextually relevant and coherent text. So if we're walking through this example, yeah, I think I talked about it. Yeah, like it's just best teacher ever. And then maybe after like it says like a period or something, ends that sentence, it'll say like she, because it'll say like, okay, Misha ends with an A, so maybe it's more likely to be like a girl's name or something. So that pronoun might be a she. And maybe after you have she, it could be like she inspires or something. So basically it's like the step-by-step process. It takes in that word, generates the next thing, takes in that thing, generates the next thing. And then it basically goes until it either exceeds the number of tokens or until that stopping condition is met. So this is really important because it has the whole context of that sequence, and it's also very fluent and coherent, and all the good things. So I think, in terms of the process, it will also have outputs that are more like safe and outputs that are like less safe. But basically you have to have both in order to be creative, right? Because if you told ChatGPT like, hey, anytime I give you a sentence, just pick the most probabilistic likely word to be the next word in that sequence, like over and over again, this would mean that ChatGPT would have like no creativity, right? Because anytime you ask it something, it's always just predicting the most probable thing. There has to be some element of creativity within models like ChatGPT or other like language learning models, right? Because if you just tell it that, then it's always going to generate the same thing all the time, and it's not going to be creative. But at the same time, it is usually safer, right, for it to use the more probably likely things, because those things are more likely to be coherent. So as you can see in this sequence, right, let's say you have like, Misha's best teacher, then maybe Ever would have like a 90% likelihood, right? But then maybe it'll just choose to go with like a 50% likelihood of like period just for creativity, and then go with 80% and then 70%, right? It's not always going with something that makes 90% contextual sense, even though, it might has something else that makes more sense, just so it can be more creative in its outputs. And that's what makes it feel a little bit more like a human, because like a human isn't just like thinking in its word, okay, like thinking in their head like, hey, I have this sentence, this thing probably makes more sense, so I'm just going to put this in. A human has creativity, right? So having this kind of level of randomness and probability enables the language model to be more kind of almost human. And it's important to also notice that while this process feels very intelligent, like ChatGPT feels like a very intelligent kind of thing, it's purely statistical, right? Because this model doesn't know, like in this case, if it's like Misha's the best teacher, the model doesn't know Misha, right? It doesn't know that Misha's the best teacher ever. But it doesn't have any like real world understanding or anything like that. But it's just generating what's the next most probable word based on the patterns that it's learned. So that's why also you should take it with a grain of salt, because as I showed you earlier with like the strawberry example, even with ChatGPT 4, people were being like, wow, this is so smart. Like this knows everything. And it couldn't even count the number of R's that are in the word strawberry, right? So that was like one example with 4. I'm sure there's examples with like 4.0 mini, 4.0 mini high, like the new versions as well. But as you can see, like even as these models get pretty smart and get really good at speaking like human and answering things properly, there's always gonna be holes because at the end of the day, you're feeding it just in terms of numerical representation. Oh, never mind. Even ChatGPT right now, if you ask it how many R's are in strawberry, says that there's 2. So yeah, it's still not patched.
I don't want mini.
She's also on mini though, so that could be it. But yeah, you guys could also take a second to try that out if you'd like. So I think I'm gonna ask, can you guys give me like an example sequence, like a sentence? Or give me like 3 words or something that go together. Like some class you're taking. I like Saturdays.
We're all gonna sit here awkwardly.
Yes, I will also say. Should I play some music or something? Yeah.
No, let's keep the awkward silence.
I'm thinking like the Jeopardy music.
The Jeopardy music.
Okay.
I think you repeat the question.
Oh. The question is, come up with like a sequence, or just like come up with a sentence.
Just a sequence of words.
A sequence of words that like make somewhat sense together.
Any sequence of words.
Yay, okay. What's a sequence?
You guys are waiting for a sequence of words.
Okay,
Wow,
awesome.
that's true.
Yes. So let's have the sequence. You guys are waiting for a sequence of words, right? What's a word that could come after that in the sentence? If someone said, okay, you guys are waiting for a sequence of words, like let's say all of you guys are language learning models right now, and someone just gave you in that input, you guys are waiting for a sequence of words. What's another word that could come after that that makes contextual sense based on that phrase I just gave you? Yeah. Because, awesome, yeah. So you guys are waiting for a sequence of words because. And then let's say you have that now, right? And I'm feeding this into the model. What could be a word that could come after that? You guys are waiting for a sequence of words because. I'll pull up the music. Yeah. Let's get one more word.
One more word.
Yeah. We're asking you guys to generate a sequence of words because.
It could be genuinely anything.
Yeah, literally.
A pronoun.
There's very little thought that has to go.
I got it.
Yeah. Because no one? Yeah. So that's a really good
actually
one.
2 words right there. Wow.
Yeah.
Impressive.
So yeah, you guys are generating a sequence of words because no one's responding, you know. But yeah, it could be something like that. So basically you're like giving in that sequence of words into like the language model, and then over time, like the language model is coming up with like, another word and it's adding that and appending that into the sentence over time. And basically it's like getting that probability. And then for that phrase, right? So you guys are generating a sequence of words. What probability do you guys think because could have in that sentence? Because in this case we picked because, right? You can throw in a random number. I'm not like verifying this. How likely do you think because could be of being that next word?
Pretty high.
Yeah. Misha said pretty high.
Anything above 50%?
Wait, let's say like out of 10, how likely do you guys think because would be the next
You
word?
can put it up on your fingers.
Put it up on your fingers, yeah. You don't have to say anything. 6, 2, 7, 4, 5, 4,
Disagreement
5.
right there.
Oh, yeah. Okay, awesome. Yeah, so something kind of like mid-level, like because would be mid-level. You guys are generating a sequence of words because, and then how likely do you guys think no one would be? You can put up on your hands. 1, 1, 6, 1, 3, 3, 3, 2. Yeah. Awesome.
Lower mid value.
Lower mid value? Yeah. And sometimes also these probabilities aren't like out of all the words in existence, like this word is like the most probable. It's also just kind of saying like this word has like a 90% probability sometimes of like making sense or like being contextually relevant in that problem. So that's, I think, kind of like the percentages that I'm usually like, I was like showing on the screen. So Yeah, and I think one question I wanted to ask you guys was, what happens if the model does predict the wrong word early on in the sequence, right? Like, let's say I have, no one is answering the question, and like, let's say instead of question, it says no one is answering the goat, or actually that makes sense. Let's say it has like no one is answering the wall. Yeah. So let's say it says wall like really early on, right? That ruins the rest of the sequence. So how could that affect the output? Yeah.
The output would just keep getting worse and worse, like further away from like an expected outcome.
Yeah, awesome. So basically, if it generates something that's not, accurate, the output would keep getting worse and worse, and that kind of messes up everything else. So yeah, that's exactly right. Like since autoregressive models rely on those previous words as input, as an incorrect word becomes part of the context, it could lead to potential cascading errors. So instead of Misha is the best teacher, it could say something like Misha's the best dancer, and then the rest of the words could be dance-relating words, right? Like it could be like best dancer because she kicks her feet or something, instead of being like she teaches, right? So this can also make the sentence illogical and confusing because as soon as you go off track, it's using that as context for the rest of the sentence, and that could disrupt the initial or original meaning. But sometimes models can recover from these errors through recovery mechanisms. So if the context is still really strong, and if you just have that one word, and that one word is like kind of the thing that's slightly off, it can sometimes realize that the intended theme is teaching, for example, based on like the previous context, and course correct. And this depends really heavily on the strength of the remaining context and the probabilistic nature of the model. So if you've seen ChatGPT thinking, sometimes it'll like give you a response and it'll start like thinking, and then it'll like change its response, right? And like correct its thing while it's generating that answer. So probably what's happening here, and I'm also, by the way, this is very hypothetical because no one really fully understands how it works. But it could be thinking about the context like over and over again, and then it's like, hey, no, actually, based on this previous context of this conversation, this answer actually makes more sense. So, and this is also where like those temperature settings are super important that I kind of had earlier in this slide. And that's why those higher temperature settings are really important, because basically it can go back and say like, hey, instead of me taking this creative outcome, let me switch back and let me do like the safe, reliable, probabilistic outcome, because, maybe that has like no error. Or, if it has like a higher temperature, basically what the temperature setting is if it's a higher temperature setting that you set for your language model, that allows for more error, and that also allows for more creativity. But that is kind of like the area where you could get on the wrong direction. So, and in real world applications, such as like summarization or dialogue generation, those early mistakes could result in outputs that deviate really significantly. So those are kind of applications where maybe you don't want to have as much creativity, right? So for example, like in customer service, or like with those customer service bots that we talked about earlier, if those bots maybe have a lot of creativity, sure, maybe they sound more human, and maybe it's, more kind of relevant to like how a human might respond. But maybe for a customer service bot, you want to really have like a really low temperature setting, because you don't want to have any chance of that customer service bot, saying something else, going fully off track and like answering some random question. So yeah, and these are some ways of mitigating it. You can have like a contextual reset where, some systems will periodically reset the context over time. So that way they're like looking at the context and resetting it to reduce the impact of early errors. Some things can be fixed through training improvements, like you can have improved fine tuning and training on diverse data sets. So that way you can handle like ambiguous or unusual inputs more effectively. And there's also some post-processing you can add as well. So like after you've made your model, you can add post-processing that adds layers of external validation that can identify that kind of incoherence in that sentence and go back and fix that. So talking about the architectures, like we're talking a lot about like these models, right? And how you guys are these models, you guys are generating these things. What are these models and what do these architectures look like? So, oh wait, okay, it's 6:02. So I'm gonna quickly wrap this up in like 1 minute. Basically, feed-forward networks. These are like the simplest types of neural networks, and they're also limited. There's like no loops, no memories. Basically, it requires all inputs to have like the same fixed length called like the context length. And basically, you're going to add like padding if it's too short for the context length, or you're going to add like truncated, which means like cut that thing. So that way it's at that level. So let's say you have like the context length of your feed-forward network being 6, and the input is I love learning AI. That input only has 4 tokens, right? So you're going to add like one padding, and then say I love learning AI. And then, yeah, those padding tokens don't have meaningful data though. So sometimes, since those are placeholders, it can mean that the model's like having to deal with things that are useless. But yeah, and also maybe I'll add some notes on this in the Discord as well. And then padding is needed, so all these inputs are the same size, so that way, it works in the model. And then this is kind of like an example of how like a feed-forward network would work, is if you had like the quick brown fox. Basically, it handles those sequences of inputs by saying like the quick brown fox, it analyzes the relationships between them, and it predicts the next word as jumps. Or an apple a day keeps the doctor away. Based on, the context of an apple a day keeps the doctor, it'll say away. So it doesn't know the full phrase, but it uses the tokens it was given. And yeah, and I will probably skip through this. Basically, another type of structure is RNNs, which are recurrent neural networks, and they have the hidden state, which is what I was talking about earlier, as how do these models remember things earlier in that conversation and have that contextual history. That's like the hidden state. And yeah, here is like the difference between RNNs and feed-forward networks. Basically, feed-forward networks always feed it forward, and it moves on to the next node. And RNNs can go back and update that hidden state over time, which allows it to be contextually aware. And yes. And here's transformers, like they're like the newest type, which is like the most cool because they work really well. They have self-attention mechanisms, which allows them to process like an entire sequence at the same time and have all that context instead of going step by step. And they replace sequential processing as a mechanism because it can evaluate the entire sequence. And yes, I think I'll probably skip through the rest of this. This is more technical anyway, and it's all covered in the technical article, by the way, the rest of these slides. So anyone on the technical track can look at this. And yeah, here's some ethical concerns where, with text generation, it can like hallucinate and, understand the wrong thing. But there could also be like the bias to generated content, which we talked about earlier, where, some language models are trained on large data sets that reflect societal biases. So if the training data has that, it could generate job descriptions maybe, and those job descriptions could be biased and reinforce stereotypes. So yeah. And then in terms of reinforcement learning with human feedback, I think I talked about that earlier, but basically what this is if you have a model that is hallucinating and it's generating that biased feedback, you can have this thing that's called reinforcement learning with human feedback. And what that means is that instead of just having the model like train and learn things on its own, the human will be giving it feedback during those training stages to make sure that it doesn't kind of go askew. So if you see like it generated a job description that looks very biased and whatever, a human can kind of give feedback to that model and say, hey, like this is biased, and fix that over time. So that's kind of what RLHF is. And yeah.